Good morning, AP Chemistry fans, and thanks for joining us again for an AP Chemistry live review session in preparation for our upcoming exam. Hope you all had a really wonderful weekend and are ready to do some exciting chemistry today. I'm Mr. Byrne from Glenbard West High School in Glen Ellen, Illinois. Our school is just coming off of spring break, so I hope we have a whole bunch of Hilltoppers that are logging in to watch us today. Today is Monday, April 6th, 2020. And we have some exciting news that we'll be able to share with you today based on some information that was released to us last week. Today's lesson will continue on our Unit 3 conversation about intermolecular forces and properties. Specifically, we're going to transition towards talking about gases and how we can both explain the behavior of gases both mathematically and explain them using the kinetic molecular theory, which is a pretty awesome tool for us to understand what's happening with gas particles. As always, as we always like to remind you, make sure that you're checking back to apcentral.collegeboard.org for all of the latest information on anything to support you or your school for AP classes moving forward. We do know, based on some information that was released on Friday, that the AP chemistry testing date for all of us is going to be Thursday, May 14th, 2020. And the way that it's going to work is that everybody will be taking the same test at the same time on their own devices. So whether you are back at school or you will be at your home, you will be taking the AP chemistry testing or the AP chemistry test at this time, whichever is your local time. So I live in Central Time, so my students will be taking the AP test at 1 o'clock p.m. But if you're on the East Coast, it would be 2 o'clock and so forth throughout here. For those of you that are watching internationally, you should be able to calculate your time based on Greenwich Mean Time down here. And so you would just calculate it based on 6 p.m. So there'll be a lot more information about what that system by which you will get the test is and how you will submit your solutions to problems back to the readers. But what you should absolutely be doing is writing on your calendar May 14th and calculating what time it is and make your plans there, because we've got an end date in sight. We've got a target that we can be aiming for to make sure that we're all prepared by then. We realize that there are lots of reasons why students might not be able to take the test at this time. And so there is an alternative testing date, which is Tuesday, June 2nd. And this is one that you would want to talk to your teacher and or the AP coordinator at your school if you needed to switch your testing date from May 14th to June 2nd. Okay, and so that's something that you would, individual students should talk to their teachers about in order to make sure that they show us their best work after all of this review time and all of the hard work you've done all year. We want to make sure that you are set up really well to be able to give us all of that great chemistry knowledge that's in your brain. Okay. So let's do a quick lesson overview. As always, we're going to do a review of our homework problems from last class. I guess this time it would be on Friday. Then we're going to talk about 3 big topics that all surround gas laws: the ideal gas law, the kinetic molecular theory, like I said, and then some deviations. So when we talk about ideal, I like to say that this is in perfect magic chemistry land where everything works out exactly how we want it to. And deviations would be in the real world. What are some assumptions we can make about how gases are going to behave when they are not in perfect magic chemistry land? Okay. As always, we'll continue to encourage you to stop when needed and make sure that if we're going too fast or we ask you to solve a question, have out a piece of scratch paper and a pencil, maybe a calculator and a periodic table as well, and make sure that you know how to solve these problems on your own. You're going to see a couple of diagrams today from that OpenStax textbook that I mentioned to you last time I was on, I think last Tuesday. It's a great open source textbook, one of many that's out there. So if you wanted to check it out, we thank them for letting us use a couple of their diagrams. Okay. So moving forward, we'll start with our warm up. some of the problems that Mr. Faribault gave us last week, where we're looking at some intermolecular forces, IMFs. Specifically, we're looking at an analysis of these 5 molecules here: pentane, propane, methanol, methanoic acid, and menthanol. And our first question asks us to explain why pentane is a liquid, whereas propane is a gas at 298 Kelvin and 1 atm. Now that's really only one part of the question. I'm going to go back to this and make sure that I highlight up here in our instructions. It says, in each explanation where a comparison is to be made, a complete answer must include a discussion of both substances. So you're going to see a series of questions here where you're asked to compare 2 different substances, but we want to make sure that we say some important things, some true things about both of the substances, not just the answer is this because of one of the molecules. Okay, so you're going to see that I like to set up my solutions by thinking about what is the same about these particles or these molecules, and then what might be different. And so for pentane and propane, they are both non-polar molecules. And I know that they're non-polar molecules because they are both a series of hydrogens and carbons. I don't see any fluorine, oxygen, and nitrogen. Those would be the 3 atoms that I'd want to look for that would immediately jump off the page for me as being polar molecules. Because we just have carbons and hydrogens in there, everything is very balanced around the molecules. These are going to be considered non-polar molecules. Okay, and so they both have are capable of having London dispersion forces, what we call LDFs, and those are those particles that, those interactions, those intermolecular forces that Mr. Faribault talked about, because of that are the result of electron displacement. And as the electron clouds are moved around, we can see that there is some induced polarity that's going to hold these molecules together. This would be a great time to stop and go listen to Mr. Faribault's great explanation of this and his awesome diagrams from Friday. If this is not sounding familiar to you. Okay, what we do know that's different about them is that pentane, because it is a bigger molecule, more carbons and hydrogens, it has a larger electron cloud. And that's a key part of this solution, that you want to make sure that we acknowledge that pentane is not just a larger molecule, but it has a larger electron cloud. And because that electron cloud is so much larger, that it will give pentane the ability to have stronger London dispersion forces. If it has larger London dispersion forces, it must have a higher kinetic energy, and kinetic energy is related to temperature. That's a conversation we'll have today to overcome these stronger London dispersion forces. And so our final conclusion might be something like, at 1 atmosphere and 298 Kelvin, propane has enough kinetic energy on average to be in a gaseous state because it has weaker LDFs, whereas pentane does not yet have enough. And so it would be in its liquid state. Here's the official answer from the College Board. So here's what I was talking about before. 1 point is earned for recognizing that pentane and propane both have London dispersion forces. But then the second point was earned for recognizing that pentane has a larger electron cloud, greater IMFs, and a higher boiling point. Okay, and so that's why it would be liquid. All right. Second problem, in a similar way, we're doing a comparison of 2 molecules. At 1 atmosphere and 298 Kelvin, methanol is a liquid, whereas propane is a gas. Okay, so now we're looking at 2 other molecules. Give you a second just to analyze what would be the same and what's different about them. What would be the same, because all molecules have London dispersion forces, we would need to say that both are capable of having London dispersion forces. But what's different is that propane only has London dispersion forces, where methanol has hydrogen bonds because of this polar side of its molecule over here. Methanol is absolutely a polar molecule because of this hydroxide group on the side. This oxygen, very electronegative, can pull on electrons really well. And because there's a free hydrogen here, we're going to have some hydrogen bonds between this hydrogen right here and the oxygens on other methanol molecules. Again, Mr. Faribault gave a great explanation of all of these intermolecular forces on Friday. I encourage you to go back and look at it. Okay, so hydrogen bonds are much stronger than LDFs, so more energy is needed to convert methanol from a liquid to a gas. So here we're doing a comparison where we're saying specific information about propane. It has only LDFs. Methanol has LDFs and hydrogen bonds. Because those hydrogen bonds are so strong, it would still be in a liquid state. 298 Kelvin on average is not enough energy to break apart, to split those particles apart take them from liquid to gas, right? So 2 points, one for recognizing the intermolecular forces, and the second for recognizing that it would take more energy. Okay. This brings us to another thing that we discussed last week about the hybridization of atoms, where we look at what kind of hybridization is around the central carbon in each of these molecules. This methanol has 4 different zones of electrons around the central carbon. And so what we can say is anytime there are 4 electron domains, that results in sp3 hybridization. I like to think that there's a 1 right here, and 1 plus 3 gives us 4, tells us that there's 4 electron domains. Mr. Faribault explained the chemistry behind this in terms of why we would have our S's and our 3 P's hybridize into 4 equal size bonds last week. So that's a great review from last week. Methanoic or formic acid has only 3 groups, 3 electron domains around it, and we define that as sp2 hybridization. Okay. Lastly, we're looking at methanoic. Or this question is asking us about the methanoate anion, but it gives us the diagram of the methanoic acid. And so the first thing we need to be able to do is to relate this anion over here to this formula that's over here, okay? And what I'm going to notice is that there's a hydrogen here that's on this side, but it's missing a hydrogen. It's an anion. This acid has a hydrogen to give. This is what we would call the conjugate base of this acid over here. So that's a good review from a number of weeks ago now, a number of lessons ago. It seems like weeks ago. So we would probably want to look at a Lewis dot structure for methanoate that looks like this with that hydrogen missing. And we should recognize that there are resonance structures for methanoate ion. So there are 2 different structures, one with the double bond bonded to this oxygen, and then we switch them. We want to make sure that we recognize that the oxygen with the double bond only has 2 electron pairs, whereas the oxygen with a single bond has 3, and that's the same can be said over here. They're just switched in a different order. Because these resonance structures are equally possible, what we would say is that the 2 bonds have the same length. So this is an example of where having a Lewis dot diagram would be a really great part of the explanation, and recognizing that these are equally responsive or equally possible gives us bonds with the same length. Okay. Lastly, this one really is last, excuse me for forgetting that we had this one coming up. We're comparing these 3 molecules. We want to have a good practice where we talk about all of them. I'm going to talk about them left from right. The carbon-oxygen bond that is right here is a single bond, so we would call that a bond order of 1. The methanoate ion, because it has these 2 identicals, like we looked at in the resonance structures on the previous slide, we would say each of these have a bond order of 1.5. And methanol over here, the carbon-oxygen bond is a double bond, which we would say is an order of 2. Okay, so just writing this out would not be enough. We would want to make a statement because they're all the same atoms, so we're all looking at carbon and oxygen. If one of these was carbon and nitrogen, it'd be much harder to compare. But we're always looking at carbon and oxygen in all 3 molecules. Bond order of 1.5 is expected to have a length that would be in between a bond order of 1 and 2. Okay, I don't know if that's in the way, excuse me. But just I'll read this to you again, because these are all between the same atoms, between carbons and oxygens. A bond order of 1.5 is between 1 and 2. Okay. So those are some our warm-up problems for today. We're going to get into what you need to know and a couple of guided practice problems. Check our time. We're doing all right here. Like I said, we're looking at 3 of the lessons from Unit 3, Ideal Gas Law, Kinetic Molecular Theory, and then any deviations from the gas law. Okay. So ideal gas law, well, the important thing to remember here is that this describes mathematical relationships. So the ideal gas law is always going to be about math. We want to pair that up with 3.4, which is the kinetic molecular theory, which explains why particles behave as they do. But the ideal gas law just tells us mathematically about some relationships. Okay, and I would assume at this point that the ideal gas law is a little bit of a review for you, but just so we have it all on one slide, let's remember that the P in PV equals nRT is equal to pressure, V is equal to volume, N is equal to the number of moles, and T is equal to temperature. This equation is given to you on your equation sheet when you're sitting for the exam. However, the more, this is an easy one to remember, PV equals nRT, and remembering what these variables are, it would be an important thing for you to be able to pull up pretty quickly. The last variable here that we want to look at is R, which is the gas constant. Now, our equation sheet gives us 3 different versions of this gas constant. And what I want you to notice is that there are different units based on how we're going to use this gas constant. So very typically in anything having to do with the gas law, ideal gas law, we're going to use the second one right in here, where our units are liter atmospheres over moles kelvins. So these have the -1s to indicate that they would be underneath. This format is sometimes a little strange for students, so I would encourage you to get used to that, and I'll show you how we're going to use it in a couple of minutes. But my hint here is always go back to this, the review sheet, or the equation sheet, excuse me, to look at what the units are listed here, just to remind yourself, okay, which units am I supposed to be using when I report my answers? Am I reporting them in the correct units as they are here? If you were to use PV equals nRT and somehow start using this number 8.314, joules is not going to fit in here really nicely, right? So it's going to, you would automatically recognize, oh, I'm using the wrong number, and then you could remind yourself to come down over here. Okay, we certainly could use, if using Tor is something that's easier for you, 62.36 is something that you want to do that. I'm much more comfortable and teach my students how to use this number, so we're going to go ahead and use that for today. Okay, so a very typical problem that you would have is that you have a container like this. It holds a certain amount of gas at 18 degrees Celsius and 1.08 atmospheres. Again, this is math. We're going to solve out for just the molar mass of this gas. Now we know we have a mass here. We need to get the number of moles. Okay, so that's N. If I can get a relationship or a ratio between this N and these grams over here, that will get me to my molar mass. So I'm going to just write out, as good mathematical practice, what's the information that I have that I know I can use, and then rearrange my equation to get me to a place where I can solve for the numbers that I want. So the problem tells me that my pressure is 1.08 atmospheres. There we go. My volume is 2 liters. My temperature is 18 degrees Celsius. And here's where I'm going to use my R from the equation sheet to see that it's liter atmospheres over moles kelvins. And that Kelvin jumps out at me, right? Because I don't have kelvins up here, and that would remind me to convert my degrees Celsius into Kelvin. It's a very common mistake that students will use degrees Celsius with this R constant instead of converting to Kelvin. I hope that we're all comfortable with adding 273 to degrees Celsius in order to get to Kelvin. So we're going to say that our temperature is 291 moving forward. I can get rid of my equation sheet now, so I have a little more room to work. I've rearranged this equation up here to say that N, our number of moles, is equal to PV divided by RT. I plug in my numbers here, do one little simplification, and should end up with a number of moles that's 0.0904. So go ahead and double check my math with your calculator if you have it. But again, the question asks us to get to our molar mass. We know that molar mass is equal to grams divided by moles. And so I should end up with something like 44.2 grams per mole. Turns out that this gas is within a margin of error of carbon dioxide, I think. It should be about 44.0. So I think if I had rounded a little bit differently, we would have gotten closer to that. But we got to a molar mass, and I would want to report that as to calculate the molar mass. Molar mass is equal to 44.2 grams per mole. Okay, so I've got a number, and I've got my units on there. Great. So that's how we would use the ideal gas law. There's many other versions of that, and I would encourage you to talk to your teacher, because I'm sure that your teacher will have other examples of how to solve that problem, or how to use that equation to solve problems. The second part that is an important piece of this lesson is to look at partial pressure of gases. And partial pressure, that means that in a sample that has a mixture of gases, the total pressure is, each component's pressure is independent of the other ones. So we're going to pretend this is, again, in ideal gas laws, perfect magic chemistry land, that the individual gas components do not affect one another. So they're partial pressures. Okay, so then the total pressure of this sample is the sum of the partial pressures. This is much easier to understand if you're looking at a picture. Okay, so if I had equal volumes of each of these three gases, whatever they are, okay, and I have a different amounts of them. So look, I have different numbers of moles in there, which means they have different pressures going from one to the other. If I were to just dump all of these into one big bottle, I would add these three numbers up, and that would be the pressure, the combined pressure in this bottle. Okay, this is a nice reminder that kPa, kilopascals, is another unit that we might use for gases. If we were looking at this mathematically instead of conceptually, we might have something that looks like this. So the total pressure is equal to the pressure from one gas plus the pressure of the other gas plus the pressure of the third gas, etc., however many there are. And if we wanted to calculate the partial pressure just for one gas, we would say the total pressure times, this is the mole fraction, right? However many moles of A we have, excuse me, as divided by the total number of moles in the container. Okay, this is an equation. These two equations are taken right off the AP Chemistry equation page. And so you should know that these will be easy for you to access if you're there. Excuse me. All right, so let's take this out for a ride and see if you're ready for some practice with this problem. We're going to pretend that we have a gas mixture that's at 0 degrees Celsius and 1.5 atmospheres, and it contains some hydrogen, some oxygen, and some nitrogen. Okay, if you are the oldest child in your family, I would like you to calculate the partial pressure for hydrogen in this mixture. If you are a middle child, what I'd like you to do is to calculate the partial pressure of oxygen gas. Oh, this should say oxygen. Excuse me, this is O2. So you calculate for oxygen gas here. And if you are the youngest child, mess that one up too, would you calculate just what the partial pressure of nitrogen is for me? Okay, and if you are an only child, you get to pick any of these three that you would like to do. I'll give you a minute either to pause or to calculate this out on your own. And a reminder that just because you're an oldest or a middle or a youngest, you can go back and practice any of these other ones however you want in the future. So I'm going to give you a solution for these. All right, so here's our equations that we're going to use, taken right off of the AP Chemistry equation sheet. And here's a reminder that for all of us, for anybody to solve that problem, what you need to do is we need to know what the total number of moles are. So we're going to start by adding up the total number of moles to get 0.05 moles of gas total in that container. And so if you solve problem number 1, where you're looking just for hydrogen, you're going to say the total pressure in the container times the mole fraction, so 0.01 divided by 0.05, and you should have gotten 0.23 atmospheres. If you did problem number 2, and again, we're looking for oxygen here, we're going to take that same point, or 1.15 times the 0.015 divided by our total. So here's our mole fraction here. We should get 0.35. And our last answer would be 0.15 times our mole fraction here. That is just for hydrogen. If I do a quick add up in my head, I think we get 1.16, which with rounding gives us 1.15. So that'd be a nice check to see if we did this right. Do they all add up to get to our original pressure that's there? Okay. So take a screenshot of this if you wanted to look at these solutions at some point in the future. Lastly, I would like to just kind of summarize a lot of the different relationships in the ideal gas law and think about how that might look in a graph. Okay, so you're gonna have to excuse some of my pictures that I drew here. There's lots of different versions of this, but we can look at 4 different relationships basically between pressure, volume, volume temperature, volume moles, and pressure temperature. Each of these relationships has a name. Boyle's law, Charles's law, Avogadro's law, and Gay-Lussac's law. You wouldn't be expected to memorize those names, but understanding these relationships between the variables would be a really important thing for you to know. And sometimes a graph is really going to help us with that. And so for pressure and volume, we're going to see that they are inversely proportional to one another. So when pressure is high, volume is low. And when volume is high, pressure is typically low. And so an example of this is if I had the same number of particles in a container, and that container got smaller, what I would see is I would have an increase in pressure, right? And the same thing would be true. I think we've all had that experience of where you're holding on to a balloon, and if you were to squeeze in on that balloon, you would feel that balloon pushing back harder on you. It's really hard to keep in your brain. There's lots of more chemistry examples of this. If you wanted to think about a piston, you wanted to think about a syringe, you want to think about some kind of a sliding box, and I'm going to show you one in just a second. But what we want to see here is the number of particles stayed the same, the temperature stayed the same. We didn't do anything with temperature, so we just made the container smaller, and so the pressure is going to get bigger. And we'll talk about why that is in a minute. Volume and temperature, which we call Charles's law. So if I have a container that I heat up, here's my little hot plate underneath here. As I heat it up, the container should get bigger. The volume could get bigger if we're going to keep pressure the same. I live in Chicago, and it's still pretty cold outside. As I look out the window, it's sunny, but it is cold. So if I took a balloon outside, I would notice that it gets smaller. So it's the opposite of this picture that I have here, right? And then if I bring that balloon from the outside to the inside, it would increase again. I'm not changing the number of particles in that balloon per se, especially if it was tied up. But as I bring it from outside where it's cold to inside where it's warm, that balloon would start to fill up again because the particles are going to fill up the space. And again, this is just looking at the mathematical representation of why this is. We're going to talk about the explanations of that in just a minute. Similarly, if I am blowing up a balloon, right? When you blow up a balloon, you are adding particles of gas into that balloon, and so it gets bigger. So the volume of it gets bigger as I add more moles. So more moles means a greater volume, smaller volume, or smaller moles means a smaller volume. Okay, it's interesting that this graph, both of these graphs seem to indicate that at 0 temperature or 0 moles, we would get to volume. We're going to talk about that in a minute as well. Okay. And then pressure and temperature is the same thing, that if I add heat to this container, right, the volume stays the same, but there's going to be pressure that is increased inside this container. And I didn't do a good job of explaining or showing you that in this picture, but what you could imagine is if we had a pressure sensor on this, you would see the pressure going up. And I will explain that to you or show that to you in just a second. So this is might be a nice picture to take or a screen to take a screenshot of. I, over spring break last week, was doing a lot of bike riding with my family, and I got to be honest that I couldn't help but think about gas laws as I was thinking about taking my bike inside and outside, and adding gas or adding air to the tires and things like that. So this is a really good example of you just being outside and looking at the tires in your car or the tires on your bike, and thinking about how gas laws are affecting those every day. I do want to jump over real quickly into a simulation that Mr. Faribaugh showed us last week that I think is a really good one. Actually, I'll show you where I got this first. Okay, I made a couple of bit.lys for you. These PhET simulations are really awesome. Whether you're a student or a teacher, they're a great resource for all of us. So go to this bit.ly. You can just do a Google search for this for PhET interactive simulations at University of Colorado, or we made a bit.ly for you with all of the simulations. I'm going to go to this one that's just on gas laws here. And we're just going to kind of explore a little bit, a couple of the ideas that are here, okay? And so what I can do is I'm going to add, yep, there we go. We're going to add some gas particles into this container, okay? And what I hope you're noticing is that the pressure is increasing as I add particles into the container, okay? And I'm going to, if I take some of those particles out, the pressure is going to go down. So we pop the balloon, right? So the number of particles, so what did we just say here? The number of particles is increasing the pressure that's in there. Does that make sense? I can close this in. So I'm decreasing the volume of the container. And what I notice is the pressure goes up again. And if I slide this out way far out here, the pressure has gone down from where it was before. Whoa, we can see that the temperature is doing some kind of crazy things here. I'm going to cool this off, right? So we get to kind of a regular temperature in here. We're just kind of playing around, and I would encourage you to do something similar. Okay, so I cooled it off, and that decreased the pressure. So we saw a relationship between pressure and temperature as well, that when I decrease the temperature of these particles, the pressure goes down, and similarly, I can increase the temperature here, and I'm going to notice what happens at a certain point. I think this is what my daughter was doing over a break. Yes, break off the lid because we got it. We've all had that experience of a aerosol can or a compressed container that if it gets too warm, we know that it can, and that's why it's real dangerous to mess around with those too much. Okay, so I'm going to get this back down to a regular temperature. What we notice is the particles are here. This is a great resource for you to just remind yourselves of relationships between all the different units. Now, I'm going to add in this idea of collisions here. And what we're going to look at are the collisions with the wall. And what I'd like you to do is, as you're looking at each of these particles, obviously this is just a simulation, right? This isn't, we can't see gas particles because they're so small. But if we could, things like this are pretty common. And if we were to look at in a sample period of 10 picoseconds, we're going to press play right here, see how many wall collisions there are at 730 Kelvin. So there are 280. So write that number down, 280 wall collisions at 730 Kelvin. And I'm going to cool us off now. Let's try to go to about half of that. Okay. We were at 280. Okay. And we got down to 190. Now, what I'm noticing here is that at a lower temperature, there are fewer collisions. And it's very important as we transition from the ideal gas law to the kinetic molecular theory, the idea behind why these gas particles behave the way they do, is that we're able to look at this and see collisions. And we see that these gas particles are both colliding with each other in the middle of this, and they're colliding with the walls. And one of the important things to see here is that the reason why there is pressure in this container, why there's pressure in any container that contains gas, is because there are collisions of the gas particles with the sides of the container. So if we can do anything to increase more collisions, or we can have stronger collisions, that we are going to increase the pressure. And I can change temperature here, I can change the volume, and what I'm going to see is there's less area here, so that's going to increase my collisions as well. And I would encourage you to just kind of play around with this as much as you can, because you'll get to see a lot more of the explanations for why these particles are behaving as they do. Okay, so let's go back into this. Okay, and we're going to go to the kinetic molecular theory, which really does a nice job of, now we're going to explain, not mathematically, but using a model and theories that are backed up by the math, but they're much more about an explanation of the particles rather than just saying, here's what the math says. So typically, when we study kinetic molecular theory, there are 5 postulates or 5 statements that are made about why ideal gases behave as they do. And the first thing relates back to that, what I just said, and we saw in that simulation, that particles are colliding with one another. They're in continuous motion. They're in straight lines until they collide with either another molecule with the walls of the container. And the pressure that's exerted by a gas is the result of those collisions. Okay, so none of this is difficult to understand, and certainly when we look at that simulation, it kind of jumps out at us. But to remember that anytime we're talking about gases, we really want to be thinking a lot about the collisions of particles with one another is an important underlying principle for you to keep in mind. Thirdly, we're going to say that the average kinetic energy of gas molecules is proportional to the Kelvin temperature. Mr. Faribaugh talked to us about that last week. We're going to look at some similar diagrams today, but we know that if there's a higher temperature, there's a higher average kinetic energy for all of the particles that's in there. The fourth and fifth are 2 statements that are a little bit tricky, and we're going to dive into when we talk about non-ideal gases. But we assume that gas particles are so small that they have a negligible volume, and certainly negligible compared to the distances that are between them. So that would be one way that simulation we're just looking at was not a good simulation, because those particles were so big compared to the container. And we know the gas particles are much, much, much smaller when they are when we compare them to this overall volume of the container. Okay, and then we also make this assumption that there's no attractive or repulsive forces. So based on our conversation last week, we know that polar molecules are going to be attracted to each other in some ways, and repelled by one another in other ways. We know that real gases, real particles, sometimes are attracted to one another and sometimes repelled by one another. But we're going to pretend, at least right now, again, perfect magic chemistry land, that none of those things exist. And so once we have that, we're going to have a little bit different explanation for each of these relationships between our variables. Okay, so what you see here is I've got a similar set of diagrams from that earlier slide, and our explanation has to talk about either collisions or particles or both. And excuse the small font here, but take a screenshot and you can zoom in later. We know that when the volume of a container decreases, the particle is going to collide with the sides more often. So I started to do that right at the end of our simulation, and you'd be able to play with that in the PhET simulation. If there's more collisions with the sides of the container, there's going to be more pressure within that container, right? So here's an explanation of a relationship between pressure and volume that doesn't just say what the graph looks like, doesn't just say a mathematical representation. It talks about what the particles are doing. It talks about how more particles are colliding with the sides. They're doing it more often. They're doing it probably stronger. And so the collisions will increase the pressure on the container. Secondly, we could look at a relationship between volume and temperature. When the temperature increases, the particles move faster, so that we know that the Kelvin temperature is related to the average kinetic energy. So we have a greater velocity in there on average. So there's more, and there are stronger collisions. You notice I have both more and stronger collisions with the sides of the container. So the volume has to increase to keep the pressure constant. So what we're saying here is, if volume and temperature are the only 2 that are allowed to change, but the pressure is going to stay the same, the volume has to get bigger in order to get to the same pressure. If we add more particles, like we're blowing up our balloon, there are obviously going to be more collisions with the sides of the container. If the pressure is not able to increase, so the pressure needs to stay the same, we're going to increase the volume in order to keep the pressure constant. So that's a great example of why when you blow up a balloon, you're inside your house, you're outside your house, the pressure in the room is not going to change. So the volume of the balloon needs to change in order to come to the same pressure as what's inside your room. And lastly, the pressure inside this container increases with higher temperatures because the volume stays the same. So we did not increase the volume in that relationship between pressure and temperature. And so we have more collisions because there's higher temperature. The pressure increases in there because the volume does not change. So here's an added explanation of these relationships. Excuse me, I'll go back to this. It's a great thing to take a screenshot of as well. On Friday, I believe, Mr. Faribaugh talked to us about Maxwell-Boltzmann diagrams. So this is a different version of that same thing, okay, where we're looking at any given temperature, right? So this is oxygen at 300 Kelvin. We have the most probable speed. So the speed has the most number of particles on it, which would be right here. And then we have what's called the root mean squared velocity or root mean squared speed. This is, we're not going to have time to go into this today, but this would be an interesting thing for you to look at and talk about with your science teacher, maybe even with your math teacher, to talk about the significance of that number that's right there. This gets interesting when we look at the same gas at multiple temperatures, right? So here's nitrogen, and what we see is the most probable speed changes, but what's really important about this higher temperature is, yes, the peak moves over to the right, but it also moves down in that we've spread out the possibility of all of these different speeds. So just because a sample of gas is on average, it has a temperature of 1000 Kelvin, doesn't mean all of the particles are moving at 750 meters per second. We still have some that are moving at a very, very low speed. We just have some that are very high so that they average each other out. So just knowing the speed of any given particle doesn't tell you the temperature of the overall gas sample, because you can see down over here, we'd have multiple gas particles within each of these groups. We need to look at the average of all of the particles that are there. And if you were ever asked to consider how one of these graphs would change as temperature changes, you'd want to make sure that lower temperatures have a much more compact curve, whereas higher temperatures have a much more spread out curve. Okay. Lastly, for the last couple of minutes, we just want to talk about deviations from the gas law. So what, as I've said, everything up until now that we've talked about has been in perfect magic chemistry land. And now we want to talk about the real world. So where are some ways that we can deviate from the ideal gas law? We want to have some reasoning. We want to justify the claim that we're going to make that ideal gases, non-ideal gases, I'm sorry, real gases will behave differently than ideal gases. So we know that the ideal gas law doesn't explain actual behavior of real gases, that there are deviations from interparticle attractions, okay, in particular conditions where they are close. And then there are also deviations or changes from gas particles, especially at high pressures. So what I like to do when I'm thinking about this is I like to go back to our ideal gases or our kinetic molecular theory and say, okay, if these are the 5 things that describe ideal gases, what might actually be different for a non-ideal gas or for a real gas? And I'm going to tell you that collisions still happen for all gases. And so the collisions are, the particles are bouncing off of one another, they're bouncing off of the walls. We also know that the pressure within a container is caused by the collisions. And we also know that average kinetic energy of gas particles stays proportional. So these three statements here do not change when we talk about non-ideal gases. What do change is these last 2. So let's talk about them just for a second. If we said that the molecules composing gas are negligibly small, well, what we know is that gas particles actually do have volume. It's not a negligible volume. And so at high pressures, which is typically low temperature or low volume or both, the volume of the particles is no longer negligible compared to the volume of the container. And so the volume of space compared to the volume of the particles, that ratio is going to change between the particles in the container, and that's what throws off our calculations. Secondly, we know that some gas particles do retract or repel one another. And at high pressures, when they're really close to one another, the attractive or repulsive forces can impact the strengths of the collisions, right? We can say that they're either going to stick to each other a little bit more so they don't bounce off each other as hard, so those collisions are not as hard, or because they're repelled from one another, we have positive sides or negative sides that are knocking into one another, they may actually push off each other even stronger in a way that would make it hard, that would make it deviate from the expected way for particles to react. Okay, so the way that this might be asked in a question is something like comparing argon to neon, where we're given a statement similar. Make sure you mention both information about both gases. Argon deviates more from ideal behavior at extremely high pressure than neon does. Okay, and so we'd want to jump into immediately is where neon and argon are on the periodic table, and noticing that neon is directly above argon on the periodic table, or we could say that argon is below neon. So going back to the trends that we talked about last week about the size of these particles, we know that argon, because it is lower on the periodic table, because it has more occupied electron shells, it would have a larger atomic radius. And because argon atoms have a larger atomic radius than neon, at high pressure and low volume, the volume of the atoms is no longer negligible. Okay, so this is where it gets a little weird though. The volume that is actually occupied by the gas is less than predicted by the ideal gas, because it takes up, because the atoms themselves take up space. So the empty space is less because the space that's filled up by the gas particles is more. So the volume, when the volume is decreased, the observed pressure is actually greater than predicted. The pressure is greater than we thought it was because the volume that was available to the particles to move around is less. Okay, so this is pretty complicated stuff, but anytime we're talking about real gases, of course, it's going to get a little bit more complicated. Okay, and I'm going to jump into our solution here real quick for our last one, because I know we're running short on time. We're looking at the pressure of a sample of methane is closer to the pressure predicted by ideal gas law than a sample of ammonia. What we're seeing here is ammonia is a polar molecule, right? So here we're going to talk about both particles. Methane is nonpolar, ammonia is polar. Much stronger IMFs present in a sample of ammonia than a sample of methane. We may even want to name those that we have hydrogen bonding that's happening here in ammonia that's not happening in methane. IMFs cause molecules to be more attracted to one another, causing fewer collisions with the sides of the container. The actual pressure of ammonia is less than the predicted pressure, okay? Because they're sticking to one another and not hitting the containers on the sides as much. So there's just two of a couple of different examples of how we could do, or how we could talk about deviations from the ideal gas law. And that brings us to the end of our lesson for today, where we talked about ideal gas law and the kinetic molecular theory. This is really where these first two are where you'd want to spend the majority of your time looking at some practice, some math problems, and then being able to do some explanations. Using that PhET simulation is a great way to do that. And then if, once you're feeling really comfortable with 3.4 and 3.5, deviations really where it starts to get interesting. Your exam practice problem for tomorrow has 4 parts to it. It's a really good summary of multiple different ideas that we've talked about over the course of these 2 weeks we've had together, a little bit more than 2 weeks now. So make sure you take a screenshot of this. We're looking at magnesium and hydrochloric acid reacting. This is some of you may have already done a reaction or an experiment like this in class. If not, we're going to walk you through what this experiment would look like and how we would solve each of these problems tomorrow. Okay, calculate the number of moles of magnesium, moles of hydrochloric acid. Here we're going to get vapor pressure just of hydrogen, and then calculate volume in liters of hydrogen gas. Okay. One more second just to make sure you've written that down or taken a screenshot. And remember that we'll start our class tomorrow with a warm-up solution to this problem. Make sure you're going back to apcentral.collegeboard.org for any questions that you have, any information that you need. We've given you a whole lot of links right below here, or we've given you a tiny URL here for other resources and other simulations if you would like to play around with them. And lastly, make sure that if you or somebody you know is having trouble with the internet or having a device, now that we know that May 14th date, we want to make sure that everybody has a device and internet access by then. If you know somebody, please have them reach out to cb.org/tech to be able to give us let us give them the help that they need. Okay, thanks for sticking with us for today. Had a great time sharing this information with you, and we'll see you again tomorrow. Have a great day.